Morning. Today I continue presentation started by Sergey in morning session. I will concentrate mostly about dynamical processes. This little diagram has the purpose to demonstrate you that there is basically a correlation between the length scales and time scale, and here as a particular target is some biological microsystem. Basically, for some event occurring at some specific time, we know, of course, a lot from the literature, and as I said, there is correlation between them. For example, to describe diffusion, we refer to time for about 10 to minus 9 seconds. To refer to protein translocation or time scale about microseconds or seconds or even longer. But there is, of course, a big number of events occurring in quite a wide range of time. And a typical example comes from ultrasonic spectroscopy, where we have non-destructive evaluation or testing and surface acoustic wave covering area for about 10 orders of magnitude. Explicit or implicit presence of time in phenomena that we are going to describe changes methods and theories that we use significantly, and I selected a few examples how we combine several different theories to describe one such kind of event. And of course, as researchers in NINT, we focus basically on nanometer scale, and it's interesting that many components of biological objects like a ordinary cell fall into the range of nano. For example, DNA, one turn, 10 base pairs, has a size of about 3.4 nanometers. Folded DNA can be as small as 10 nanometers. RNA is about the same order of size. Ribosome is a little bit larger. This is a typical virus of influenza called a star influenza. I have no idea if it is more dangerous than swine flu. Yeah. Secretory vehicles about 200 nanometers, and perhaps the last large object that fits into nanometer scale is mitochondria, about half a micron. And my example, how do we use theory to describe time-dependent phenomena, I would like to start from this picture that many of you could remember already from the school age, or at least first or second year of engineering faculty in university. This is the velocity profile for liquid flow between channels or in a pipe. The background that I should say for this research is coming, or idea to do this research on a nanometer scale is dictated by the demand from development of devices for biomedical analysis. There is a large demand on the market now for biomedical analysis devices, and one such kind of device was constructed and produced by our colleague at the University of Alberta, Department of Chemistry, Professor Jed Harrison and people from his group. On the micrometer scale, they succeeded to produce a kind of microporous matrix, or sometimes it goes into the range of nanoporous matrix, that is used to separate proteins of different lengths. That can be useful, for example, for blood analysis in a clinic, or just for biomedical analysis of different kind. And since the flow of these polymolecules and proteins and DNAs occurs in a nanoporous and microporous matrix, we have to use equations of fluid mechanics to describe them. Of course, fluid mechanics is one of the oldest branches and is very well known, but when we go to the small scales, micro or nano, boundary conditions become very important. And if you see, this is the line for velocity profile arrows represent the amplitude for the velocity. When we refer to fluid mechanics on large scales, like for ship or aircraft flying, typically people draw this velocity profile like this, so there is complete decay velocity on the boundary, but as a matter of fact on small scales it doesn't happen that velocity decays instantly to zero. If we extrapolate inside of the boundary material, we will obtain some distance delta called the slip length, and this boundary value has to be specified very precisely in order to describe the fluid flow on that nanometer scale. And if you make very little mistake, say just a couple of nanometers or even micrometers, the characteristic or characterization of the material you use for that nanoporous matrix changed very significantly, and you may obtain results that can be misleading. So we have to solve the problem, for example, for that particular case, to calculate this distance slip length. For that purpose, we combine some existing theories that we have already and something that we developed. It is a linear response theory, theory of molecular solvation, fluid mechanics, quantum chemical computations to obtain some parameters to describe molecule geometry and partial charges. And we verified it for a bunch of different liquids. First of all, water, because water is number one for the solvent in this case. Then methanol, ethanol, acetonitrile, dimethyl sulfoxide, ethanol amine, glycerol, terbutyl alcohol, and of course benzene. And immediately we obtain something new, something that could not be obtained from phenomenological description that doesn't involve molecular specificity. What is that? This diagram is a slip velocity or boundary value versus viscosity of the solvent used, and according to what is known, this dependence has to be more or less monotonous. If you take more viscous liquid, then the boundary condition should dictate larger value for the slip length. We have some deviations. For example, water doesn't fit, alcohols also don't fit. Phenomenological studies anticipate only monotonous behavior, while molecular theory can predict deviation from that due to, in particular, ability of some liquids to create hydrogen bond networks. Then, as a bonus material, we also obtain a distribution of liquid with specific information for interaction site near the surface. For example, this picture is a distribution of dimethyl sulfoxide at a gold surface. The gold surface is assumed to be flat here, and for each site we have different probability to find the site near the surface. We also can obtain information about which molecular layer contributes most for the friction. That information can be vital for those people who want to do the same type of research using molecular dynamic simulation, because they get the idea how many molecular layers they can take to form their simulation box. However, one has to be very careful with that, because first molecular layer, which is molecular solvation shell near the surface, is formed by about 10 or more another molecular layers away from the surface, and all of them have to be taken into account.